Okay, welcome back. This is the continuation of the second video of the 30th week when we are discussing network sampling, and so far we have already discussed approaches from social sciences that are intended for sampling hidden population, but as a side effect they also give you a bias sample of a social network. And we talked about some classical computer science techniques for sampling, specification, or simplification, and so on, and how well they perform in different scenarios. So, what we are left with are the approaches that try to study the fractal structure or self-similarity of real networks. And how is fractal structure defined? Fractality is defined to be a property of some geometric object that is similar to itself or to a part of itself. Now, there are papers on fractal networks that are linked to EU-Cilica. If we go a step further, self-similarity actually demands a bit more. And in particular, the classical theory of self-similarity demands some power law scaling under some renormalization process. And by renormalization, you can simply see that as a merging or aggregation techniques, like for instance detecting communities and then merging them into individual nodes. So you take your entire network, you find some reasonable parts that can be communities or something else, and you merge this into single nodes and get a smaller network. In the theory of self-similarity, the most popular approaches will be like box covering, cluster growing, tiling approaches, and so on, when you try to tile or cover your network with some boxes or tiles of a particular size. So you specify what is the maximum number of nodes in each tile, or what is the maximum distance between the nodes in a tile, and so on. So then you can run this renormalization technique with different sizes of these tiles, and you can plot on the horizontal axis the sizes of the tiles, and on the vertical axis the number of the tiles that you get. And in order to say that the network is self-similar, this should follow a straight line on a doubly logarithmic plot. So basically that there should be a power law relation between the sizes of the tiles or boxes or so on and their number. And again, you can find papers on EU-Cilica that deal with exactly that. Now, what I want to discuss now is maybe some more empirical results on network self-similarity, and in particular we will deal with density of network and later with the community structure. So firstly, regarding the density, there was a paper 10 years ago showing something they called a self-similar density of real networks. Meaning that we know that real networks are sparse, and they actually shown that the density follows a power law relation with the size of the network. So remember, the density of the network will simply be the number of links divided by the number of all possible links, or equivalently the average degree divided by the number of nodes in a network. And then you can plot. The authors took like 100 different networks, and for each they have plotted their size, the number of nodes, and their density. And it turns out that this plot roughly follows straight line on a double logarithmic plot. So again, we have a power law relation, and the exact formula that you get is that the density is something very close to 7.89 times n to the power of minus 0.99, almost to the power of n to the minus 1, which is, and looking at both of these two formulas, what you can actually see is that the average degree in the network is relatively constant throughout different sizes of the networks. So smaller networks are denser than larger networks. All are sparse, but still smaller networks are obviously denser than larger networks. However, they follow a particular power law scaling. Meaning that it's unlikely to observe a network that will have a degree that will scale in some way with the size of the network. Now, we went in our work 10 years ago, we went a bit further and tried different network renormalization techniques, so like box covering, cluster growing, and also the approaches that we mentioned before, like aggregation or merging approaches. These are these approaches here, when you, for instance, detect the communities in a network and then merge all the nodes in a community into some supernode, get a smaller network, you repeat the process, and so on. So what are the results that we get? Here the plots are showing you for the three different renormalization techniques. Firstly, the density of the networks of different sizes, which is here shown with this green triangle. So we are constructing exactly the same plot as on the blackboard. And you can see that it roughly follows a straight line. Then what we have done is that we have used some renormalization technique like community aggregation to get smaller and smaller networks, and also plotted their density and size on the same plot. These are these blue circles here on the plot. And you can see that it still retains some nice power law scaling. Basically saying that under any of these renormalization technique, the network density is invariant. So it follows this formula so that the density is very scales as n to the power of minus 1. And this result is not obvious at the beginning, because it may happen then when you are merging the nodes in communities and make the network smaller, it could be that the network will become denser or sparser. You might be getting a full graph or a tree graph or so on, but it turns out that it still follows this nice relation. And as a practical maybe application of that, here on the right hand side, I am showing you a wiring diagram of three large networks that are all in millions of nodes that we have normalized using this procedure to get a smaller network, and I have drawn this network. And for instance, if you take the web graph of Notre Dame, notice that it's still this smaller sample that contains only of a couple of hundred of nodes, that is several orders of magnitude smaller than the original network. It still retains some properties that we know that are present in web graphs. Like for instance, here some nice core periphery structure. Or at the bottom, you can see a road network of roads in Pennsylvania, and you can see that since the network is spatial network, so nodes have some specific positions. This spatial structure is largely retained you get roughly a grid-like graph here. I'm not sure whether the Pennsylvania looks exactly like this, but looking at both of the two examples, you can see that the large-scale structure of the network is largely retained under this normalization procedure. Okay, so this is regarding the density. So the network density of real networks can be said to be self-similar. We follow some nice formula, and this is also retained after some renormalization, like for instance detecting communities and aggregating them. So if we go a step further, and talk a bit more about community structure. Let me explain this on the blackboard. We know that many real networks show some nice community structure, which is probably also one of the main reasons why the community detection and development of different community detection algorithms have been so popular in, say, around the year 2010 and so on. And we have developed an approach for community detection that is similar like block modeling or stochastic block models that can detect not only communities but also any other type of structure. And how the algorithm works is that it finds individual clusters or communities in a network that are most pronounced and extract them from the network and then repeats the process to find the next most pronounced community or cluster and so on. So imagine that I found a certain cluster of nodes. Not only that I detect the cluster, I also separately detect where these nodes in this cluster primarily connect to. So where do they live? So for instance, imagine that all of these nodes are linked to external nodes here on the right. So we have found roughly a bipartite-like structure. We are calling this left the cluster, or the actual group that we want to detect, whereas this right set of nodes, I'm calling it the focus of that cluster. So where does this cluster primarily connect to? And so for each group or cluster, I also get its focus, which is again just a set of nodes. And most of the links are between the cluster and the focus. If I get a result like the one shown on the blackboard, where the cluster is completely disjoint from its focus, you will get a roughly bipartite structure. For instance, if we go on, and let's say that I find a cluster where this cluster mostly connects to itself, so it forms a community, its focus will be the same set of groups. So if the focus and cluster largely overlap, so I'm roughly finding the community structure. Imagine that I find some group of nodes that primarily connects to some sub part of this group of nodes. So the focus is a subset of the cluster. What I have found is basically a core periphery structure, and so on and so forth. So knowing the cluster and the focus, I can actually say something about what kind of groups that I have found. Or and in particular, we will be looking at the cluster and its focus, and I will look at its intersection, and I will measure the Jaccard coefficient of the cluster and its focus. So that will be the size of the intersection divided by the size of the union. And I will denote this value with tau. And why would that be useful? Because if I have a certain cluster and it's focused, I can compute this tau and tells me something about what kind of groups I have detected. If tau is close to 1, meaning that C and F overlap, I found a community. If tau is close to 0, meaning that C and F are disjoint, I found a bipartite structure, and so on. So the values of this tau are basically telling me how community-like clusters I have found. If tau is close to 1 or if tau is larger, I get more community-like clusters than if tau is close to 0. And these small figures here at the bottom try to show different groups and focuses that I can detect. So for instance, here I have the green nodes are the group, and this node with the triangle within is its focus. What I have found is hub and spokes arrangement. The second example shows you what I have drawn before on the blackboard, a simple bipartite structure. You have a group in the middle that primarily connects to some other group of nodes. Here you can see an example of a community. Here you can see an example of a core periphery structure, and so on. So not going into any further details regarding this algorithm, I want mostly show you the results. So we know that most networks have a pronounced community structure. Sorry. So this algorithm will reveal communities or clusters with tau that will be close to 1 or much higher than 0. And here at the bottom, these plots are showing you results for 3 networks. And for each network, I am detecting these clusters, and then I'm computing their taus, and I am plotting the histogram of taus on this plot. And notice for a citation network, if I take the entire network, these are these black bars, notice that most of taus are close to 0. So I do not get community-like groups. In the case of a social network or a collaboration network, these taus are around 0.5, say, or something like that. So I get more community-like structure in those networks. And this is expected because we know social networks will have a pronounced community structure. Now, what we did next is we use different sampling techniques like random selection techniques, exploration techniques, aggregation techniques, and so on, sample the network, make the network smaller, and again detected the groups, computed the taus, so that we can see what kind of groups are we getting now. And notice that these gray bars corresponds to different sampling approaches, and notice that in all cases, these gray bars are more shifted to the right, meaning that under any sampling technique that I have used, community structure was more pronounced than in the original network. So basically saying that the community structure the sampling enhances the community structure of a network. So if I don't take the entire network, but just in sample, its communities will probably be more pronounced than in the original network. And why would this result be interesting is that at the beginning I said that most of the networks have a nicely pronounced community structure. People have found communities in almost any type of networks. What these results are telling us that this could be just a property or a consequence of sampling, because most of the networks that we analyze are simply samples, and when I take a sample, the community structure becomes more pronounced. So maybe that all communities that we're seeing in real networks, or some communities that we're seeing in real networks, or people have found in and reported in the literature, could only be a consequence of sampling, not really a property of the original network. So we have learned something about how sampling changes the structure of a net. Okay, this is more or less what I wanted to say about network sampling. We will deal more with this in labs. And as I said at the very beginning, this is still, as you can also see from the results, an unsolved problem in network science. And this is one of the two topics that we expect that, say, in the next 10 years, hopefully will be at least to some extent solved. First is the sampling, and second is how to deal with noise in network data, and both problems are to some extent related. Okay, so that's it. Thank you for listening, and see you in